Hello everyone and welcome to the Plantagen team's presentation for the 2025 Gen Hackathon sponsored by BNP Paribas and Institut Polytechnique de Paris. Our project is titled Urban Heat Islands and Climate Downscaling, and today we will be presenting our work on this critical urban challenge. Our challenge for this period was to explore the urban heat island or UHI effect. The goal wasn't just to observe it, but to model it by integrating diverse data sources, specifically Era 5 climate data, Sentinel-2 vegetation maps, and ground station observations. Our objectives were clear. First, to quantify heat stress beyond simple temperature. Second, to combine variables like heat, dryness, and vegetation into a single comprehensive score. And third, to validate our features against reliable ground truth data from the EC&D station network. Before any analysis, we had to define our study area. We used the GADM database to auto-detect the administrative boundaries for our target city, Utrecht in the Netherlands. By searching the administrative levels and then dissolving the internal polygons, we created this precise unified boundary you see here. This area of interest, or AOI, is the foundational map we used to clip and spatially average all our subsequent climate and satellite data. On the left, we have Era 5 land climate data, which provides daily variables like temperature and wind, here shown as the U10 or zonal wind component over Europe. In the middle, we have our vegetation data from the Sentinel satellites, shown as quarterly NDVI sample from Utrecht. Greener areas indicate healthier vegetation. Finally, on the right, the map shows our key harmonization step, reprojecting the low resolution Era 5 temperature data onto the high resolution NDVI grid. This pixel alignment is crucial for our analysis. With our raw data collected, the next critical step was harmonization. We couldn't compare daily climate data with quarterly vegetation data directly, so we processed everything into a single monthly feature matrix, which you see in these plots. We aggregated the daily Era 5 data like max temperature, precipitation, and wind into monthly means. We then joined this with our vegetation data using the monthly Sentinel-3 NDVI in purple and filling any gaps with the quarterly Sentinel-2 data in brown. This final harmonized table is the backbone of our entire analysis, covering the period from 2020 to 2025. Here we are looking at our Sentinel-2 quarterly NDVI. NDVI, or the Normalized Difference Vegetation Index, is our proxy for greenness. As you can see, it shows a very clear and stable seasonal pattern. The city is greenest in the summer and vegetation is lowest in the winter. This was a reliable, high-resolution dataset, but we used it primarily as a fallback to fill gaps in our monthly data. Our primary greenness signal came from the Sentinel-3, which provides a monthly mean NDVI. This plot shows the same annual phenology, the greening in summer and dip in the winter, but with more temporal detail. This monthly resolution is what allows our final UVHS score to be highly responsive to environmental changes, like a sudden drought or browning event. A key part of our project was validation. We couldn't just trust the Era 5 climate model, we had to check it against the ground truth data. Here, we compare our Era 5 daily max temperature, the blue line, against historical data from ECA&D weather stations near Utrecht. As you can see by zooming into the 2020 to 2025 period, the Era 5 data tracks the ground station data, like the orange line from the DEVILT station, with extremely high accuracy. This confirms our choice of climate data is reliable. To perform that validation, we first had to find the stations. We loaded the ECA&D station metadata and spatially joined it with our Utrecht polygon. This identified 4 stations located inside the boundary. We selected the most central and complete one, DEVILT station 162, shown here in blue, as our primary source for ground truth validation. The final deliverable for our pipeline is this harmonized monthly feature dataset, shown here as a schema. A single clean table contains the monthly averages for all our key variables: T2M maxi for heat, TPMM day for dryness, our S3 and S2 NDVI values for greenness, and most importantly, the final UVHS score. This dataset is now ready for any further analysis, modeling, or visualization in a dashboard. The notes on NDVI also help clarify how to interpret the greenness values. This project demonstrates a robust data-driven approach to quantifying urban environmental stress. By integrating diverse data sources, we can create actionable metrics to help build more resilient and livable cities. Thank you, and we are the Pentagon team.